This is the EdExcel Advanced Extension Award in Mathematics paper from the June 2023 series. Question 1. Part A. Write down the exact value of the cosine of 405 degrees. For Part A, to find out what the cosine of 405 degrees is, we can begin by thinking about the cosine of 45 degrees. And because cosine is a periodic function and repeats every 360 degrees, if we find out what the cosine of 445 degrees is, adding 360 degrees to 45 degrees and then finding out the cosine of that result is the same as finding the cosine of 405 degrees. So the cosine of 45 degrees, that's equal to root 2 over 2, and therefore the cosine of 405 degrees is equal to root 2 over 2. Part B. Hence, using a double angle identity for cosine, or otherwise, determine the exact value of the cosine of 101.25 degrees, giving the answer in the form a times the square root of b plus c times the square root of 2 plus root 2, where a, b and c are rational numbers. Now let's think about the link between the 405 degrees and the 101.25 degrees. If I halve 405 degrees, I get 202.5 degrees, and if I halve 202.5 degrees, I get 101.25 degrees. So it makes sense for me to use the double angle identity for cosine. Now, if we think about the identity cos squared x equals 1/2 multiplied by 1 plus cos 2x, if I square root this, I end up with cos x equaling plus minus the square root of 1/2 multiplied by 1 plus cos 2x. And it makes sense for me to use this identity because this angle x is half of the angle 2x. We have square roots involved, which is what I will show that requires. And we also have the graph of cosine x in between 0 and 360, which we will use as a reference throughout the question. Now let's think about finding out what the cosine of 202.5 degrees is. That's equal to negative, and the reason it's negative is because 202.5 is in between 90 and 270. Then we have the square root of 1/2 multiplied by 1 plus cosine of 2x, so we have 1 plus the cosine of 405 degrees. Doubling the 202.5 degrees gets us the 405 degrees. So we have negative square root of 1/2 multiplied by 1 plus root 2 over 2. And if we attempt to simplify this even further, we have the negative square root of, now if I factorize out a 1/2 from this bracket and then multiply that by half, I get a quarter, and then inside the bracket we would have 2 plus root 2. And if we simplify even further, we have negative 1/2 multiplied by the square root of 2 plus root 2. If I now think about the cosine of 101.25 degrees, well, 101.25 degrees is in between 90 degrees and 270 degrees, so will be negative So we have negative the square root of 1/2 multiplied by 1 plus the cosine of 202.5 degrees. And you already know what the cosine of 202.5 degrees is. That's negative 1/2 multiplied by the square root of 2 plus root 2. So we have negative the square root of 1/2 multiplied by 1 subtract 1/2 multiplied by the square root of 2 plus root 2. Let's attempt to simplify. We have negative the square root of, now if I factorize out a 1/2 from this bracket and multiply it by 1/2, I end up with 1/4, and inside the bracket we would have 2 subtract the square root of 2 plus root 2. And so we have negative 1/2 multiplied by the square root of 2 subtract the square root of 2 plus root 2. We can conclude from this A is equal to negative 1/2, B is equal to 2, and C is equal to negative 1. Question number 2. A student is attempting to prove that there are infinitely many prime numbers. The student's attempt to prove this is in the box below. Assume there are only finitely many prime numbers, then there is a biggest prime number, p. If we let n equal 2p plus 1, then n is bigger than p, and since 2p plus 1 is not divisible by p, n is a prime number. Hence, n is a prime number bigger than p, contradicting the initial assumption, so we conclude there are infinitely many prime numbers. Part A, use p equals 7 to show that the following claim made in the student's proof is not true. Since 2p plus 1 is not divisible by p, n is a prime number. So for part A, if we think about p equaling 7, n will then equal 2 multiplied by 7 plus 1, which is 15. Although 15 is not divisible by 7, 15 is equal to 5 multiplied by 3, so it's not prime. So the claim is not true. The student changes their proof to use n equals 6p plus 1 instead of n equals 2p plus 1. For part B, we have to show by counterexample that this does not correct the student's proof. Well, for part B, if we think about p equals 19, n is equal to 6 times 19 plus 1, which is 115, and 115 is the same as 5 times 23, so it's still not prime. So we can conclude then that using 6p plus 1 does not correct the proof. Part C, write out a correct proof by contradiction to show that there are infinitely many prime numbers. For part C, we assume there are finitely many primes. And if that's the case, then we can write a complete list of primes. If we let p1, p2, etc. all the way up to pn be a complete list of primes, then what we will do is consider a new number, n equals p1 multiplied by p2 multiplied by numbers all the way up to pn plus 1. So we have the product of all the prime numbers plus 1. That's what our new number is. Now, the reason we add 1, well, as 1 is not prime, adding 1 gives a remainder of 1, which ensures none of these prime factors, p1, p2, etc. up to pn, divide into this new number n. So if we consider this number n, either n is prime or n is not prime. So if n is prime, then n is not in this list of original prime numbers that we saw here, because we are saying this is a complete list of prime numbers. But if n is prime, then we have a number which is not in that list. And this would be a contradiction. So that's because P1, P2, etc. up to Pn is a complete list of primes. Now if n is not prime, through the factor decomposition, n has a prime factor which must be a factor of 1, which is impossible because 1 only has factors of 1 only. So this is also a contradiction. And because we have a contradiction, that means our original statement which is that there are finitely many primes is false. So there are infinitely many primes. Question number 3. Figure 1 shows the curve C given by the parametric equations x equals 5 over root 3 sine t, y equals 5 multiplied by 1 minus cos t, where t is in between 0 and 2 pi. The circle with centre at the origin and with radius 5 root 2 over 2 meets the curve C at the points A and B as shown in figure 1. So we've got this curve C, we've got this circle which meets the curve C at the points A and B. We have to determine the value of t at the point B. So what we know so far is x equals 5 over root 3 sine t, y equals 5 multiplied by 1 minus cos t, and the circle has radius 5 root 2 over 2. So for part A, we've got the equation of the circle being x squared plus y squared equals radius squared. So we have x squared plus y squared equals 5 root 2 over 2 squared. And if we simplify, x squared plus y squared equals 25 over 2. I know what x is, I know what y is. So we have 5 over root 3 sine t squared plus 5 multiplied by 1 minus cos t all squared equals 25 over 2. Let's try to simplify this as much as possible. We have 25 over 3 sine squared t plus 25 multiplied by 1 minus 2 cos t plus cos squared t. This is equal to 25 over 2. And if I multiply through by 6 over 25, well, we have then 2 sine squared t plus 6 subtract 12 cos t plus 6 cos squared t equals 3. And let's try to simplify this and solve. If I replace the sine squared with an appropriate identity, we have 2 multiplied by 1 minus cos squared t, and then we have plus 6 subtract 12 cos t plus 6 cos squared t equals 3. So we can simplify this to 4 cos squared t subtract 12 cos t plus 5 equals 0. We can factorize this as 2 cos t subtract 1 multiplied by 2 cos t subtract 5 equals 0, in which case we see t is equal to 1/2, or cos t doesn't equal 5 over 2, which means then cos t equals 1/2 is our only solution, and at the point B x is positive, which means then t is equal to pi over 3. So at the point B, t is equal to pi over 3. The region R, shown shaded in figure 1, is bounded by the curve C and the circle. We have to determine the area of the region R. The parametric area is given by the integral from mu to lambda of y multiplied by dx over dt multiplied by dt. Dx over dt is equal to 5 over root 3 cos t. And so, for our area under C, the way we can think about this is to think about this portion on the first quadrant and then doubling it because of symmetry. So we have 2 multiplied by the integral from 0 to pi over 3 of 5 multiplied by 1 minus cos t multiplied by 5 over root 3 cos t dt. So let's try to simplify this and work this out. Well, we've got the 2 times by the 5 times by the 5 over root 3, which is 50 over root 3. And then we multiply this by the integral from 0 to pi over 3 of, well, we have 1 minus cos t multiplied by cos t, which is cos t subtract cos squared t. And we're integrating this between 0 and pi over 3 with respect to t. So, if we simplify even further, we've got 50 over root 3 multiplied by the integral of, well, we've got the cos t subtract, and this cos squared t I'm going to replace with 1/2 multiplied by 1 plus cos 2t dt, and we're integrating between 0 and pi over 3. So we've got 50 over root 3 multiplied by, well, if I integrate cos t, end up with sin t. Integrating negative 1/2 times 1, end up with negative t over 2. And integrating negative 1/2 cos 2t, end up with negative sin 2t over 4. And this is to be evaluated between 0 and pi over 3. So we have 50 over root 3, and if I substitute in pi over 3, well, substituting pi over 3 into here, we have the sine of pi over 3, which is root 3 over 2. Then we have negative pi over 3 over 2, which is negative pi over 6. And then we have negative sine 2 times pi over 3 over 4, which is negative root 3 over 8. And so, simplifying, we end up with 50 over root 3 multiplied by 3 root 3 over 8 subtract pi over 6, which simplifies to 75 over 4 subtract 25 pi over 3 root 3. What we can now do is determine the values of the coordinates of a and b. So when t equals pi over 3, x is equal to 5 over root 3 times by the sine of pi over 3, which is 5 over 2, and y equals 5 multiplied by 1 minus the cosine of pi over 3, which is equal to 5 over 2. Which means then, through symmetry, a is equal to negative 5 over 2, 5 over 2, and b equals 5 over 2, 5 over 2. So, if we add this to a diagram, we've got the coordinates of a negative 5 over 2, 5 over 2, and b with coordinates 5 over 2, 5 over 2. And we've got these other regions which we can work out the area to help determine the area of R. First of all, we can work out the area of the sector OAB. So, we know what the radius is, so we have 1/2 times by the angle pi over 2, and that's because we have a V shape and this angle is 90 degrees, multiplied by 5 root 2 over 2 squared, and if I work this out, I get 25 pi over 8. We can work out the area of the triangle AOB, that's equal to 1/2 times by the base times by the height. So we have 1/2 times by 5/2 times 5/2, which is 25/4. Then we've also got the area of this rectangle, which is 5 times by 5/2, which is 25/2. So we have 5 times by 5/2, which is 25/2. And now what we can do is find out the area under this circle. So that area is equal to the 25π/8, which was the sector, subtract the area of the triangle 25/4 plus the area of the rectangle 25/2, and working this out we get 25π/8 plus 25/4. So now that we know what the area under the circle is, the shaded area R, that's equal to the area under the circle 25π/8 plus 25/4, and then we subtract what we worked out previously, the area under C, which is 25/4, subtract 25π/3√3. So let's try to simplify this. What we end up with is 25π multiplied by 1/8 plus 1/3√3, subtract 25/2, which would simplify to 25 multiplied by 9 plus 8√3/72 multiplied by pi, subtract 1/2. Question number 4, part A. We have to use the trapezium rule with 4 strips to find an approximate value for the integral of 16 to the x with respect to x between 0 and 1. So, for part A, if we let y equal 16 to the x, let's create a table of values. Now we have 4 strips, so if we start off with x equaling 0, the next value of x we require is 1/4, the next value of x we require is 2/4, the next value of x we require is 3/4, the next value of x we require is 1. To find the corresponding y values, we substitute back into y equals 16 to the x. So 16 to the 0 is 1, 16 to the 1/4 is 2, 16 to the 2/4 is 4, 16 to the 3/4 is 8, and 16 to the 1 is 16. And what you will notice is we are going up in quarters each time for our x values. So using the trapezium rule, the integral of 16 to the x with respect to x between 0 and 1, that's approximately equal to, well, we have 1/2 times by 1/4 times by 1 plus 2 multiplied by the values in the middle, so we have 2 plus 4 plus 8 plus the final value 16, and if I work this out I get 5.625. Part B used the trapezium rule with n strips to write down an expression that would give an approximate value for the integral of 16 to the x with respect to x between 0 and 1. So let's start with creating a table of values. Now we are going from 0 to 1 with n strips. So we have 0, 1/n, 2/n, etc. Then we have n minus 1/n, finishing off with n. And what you will find is we are adding 1/n each time. So now, to find the y values, we know that y is equal to 16/x. So when x is 0, y is 1. When x is 1/n, y is 16/n. When x is 2/n, y is 16 to the 2/n. And then we can continue with this. Then when x is equal to n minus 1/n, y equals 16 to the n minus 1/n. And then when x equals 1, y equals 16. So now what we can do is use the trapezium rule. So we have the integral from 16 to the x with respect to x from 0 to 1 being approximately equal to 1/2 multiplied by 1 over n multiplied by, well, we've got our first term 1 plus twice the middle terms, so we have 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n, and then we add on the 16. So if I simplify this, we end up with 1 over 2n multiplied by, now here we've got the 1 plus 16, which is 17, and then I add 2 lots of 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n. For part C, hence, show that the integral of 16 to the x with respect to x from 0 to 1 is equal to the limit as n tends towards infinity of 1 over n multiplied by 1 plus 16 to the 1 over n plus terms up until 16 to the n minus 1 over n. So for part C, we've got this integral of 16 to the x with respect to x from 0 to 1, and if we use our answer to part B, we've got the limit as n tends towards infinity of 1 over 2n multiplied by 17 plus 2 multiplied by 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n. So if I factorize out a 1 over n, inside I would have a half times by these terms here, so I would have the limit as n tends towards infinity of 1 over n multiplied by 17 over 2 plus 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n. And notice the 1/2 times by the 2 gives the 1. Now I'm going to rewrite what we have here as the limit as n tends towards infinity of 1 over n multiplied by 17 over 2, subtract 15 over 2, plus 15 over 2, plus 16 to the 1 over n, plus 16 to the 2 over n, plus terms up until 16 to the n minus 1 over n. And what you will find is that the negative 15 over 2 plus the 15 over 2 is 0. So I'm adding 0 to 17 over 2 essentially. So what we end up with here is the limit as n tends towards infinity of 1 over n multiplied by 15 over 2. And then I add on to this the limit as n tends towards infinity of 1 over n multiplied by 17 over 2, subtract 15 over 2, plus 16 to the 1 over n, plus 16 to the 2 over n, plus terms up until 16 to the n minus 1 over n. So now I recognize that the result of the limit as n tends towards infinity of 1 over n multiplied by 15 over 2 is just 0, leaving me with 1 over n multiplied by 1 plus 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n. And notice 17 over 2 subtract 15 over 2 gives 1. Part D, use integrate to determine the exact value of the integral of 16 to the x with respect to x between 0 and 1. So the integral from 16 to the x with respect to x between 0 and 1, that's equal to 16 to the x over the natural log of 16. We're evaluating this between 0 and 1. So when I substitute in 1, I get 16. When I substitute in 0, I get 1. So I end up with 15 over the natural log of 16. Given that the limit exists, for part A we have to use the answer to part C and the answer to part D to determine the exact value of the limit of 16 to the x subtract 1 over x as x tends towards 0. So if we use the result to part C, we have the limit as n tends towards infinity of 1 over n multiplied by 1 plus 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n. So if we use part C, let's consider the 1 plus 16 to the 1 over n plus 16 to the 2 over n plus terms up until 16 to the n minus 1 over n. We can rewrite this result as the following. We've got 1 plus 16 to the 1 over n plus 16 to the 1 over n squared plus terms up until 16 to the 1 over n to the n minus 1. What we have here is a geometric series with a, our first term, equaling 1, and r, the common ratio, being 16 to the 1 over n. So the sum of these terms we can find out. We have 1 multiplied by 16 to the 1 over n to the n, subtract 1, and then we divide this by 16 to the 1 over n, subtract 1. Now 16 to the 1 over n to the n is just 16, so we have 16 subtract 1, which is 15, and multiplying that by 1, we get 15. So we have 15 over 16 to the 1 over n, subtract 1. And if we use the result to part C, I know what this bracket is, I've just worked that out. So I've got the limit as n tends towards infinity of 1 over n multiplied the result of this bracket. So I've got the integral of 16 to the x with respect to x from 0 to 1 equaling the limit as n tends towards infinity of 1 over n multiplied by 15 over 16 to the 1 over n subtract 1. Now in part D we found that the integral of 16 to the x with respect to x between 0 and 1 is equal to 15 over the natural log of 16. And if we set these equal to each other, we've got 15 over the natural log of 16 equaling the limit as n tends towards infinity of 1 over n multiplied by 15 over 16 to the 1 over n subtract 1. So we've got 15 over the natural log of 16 equaling 15 multiplied by the limit as n tends towards infinity of 1 over n over 16 to the 1 over n subtract 1. And the 15's cancel on both sides, leaving us with 1 over the natural log of 16 equaling the limit as n tends towards infinity of 1 over n over 16 to the 1 over n subtract 1. Now, if we let x equal 1 over n, then as x tends towards 0, as n tends towards infinity, which means as the limit exists by continuity, we have 1 over the natural log of 16 equaling the limit as x tends towards 0 of x over 16 to the x subtract 1. And if we think about what we want to show that the limit as x tends towards 0 of 16 to the x subtract 1 over x. That's what we want to find out, and that's just the reciprocal of what we have. So if we reciprocate, we'll find the limit as x tends towards 0 of 16 to the x subtract 1 over x is equal to 1 over the natural log of 16, which is just the natural log of 16. And therefore, the result is equal to the natural log of 16. Question number 5. Figure 2 shows a partially completed Venn diagram of sports that a year group of students enjoy, where A, B, C, D and E are non-negative integers. The diagram shows how many students enjoy a combination of football, F, golf, G, and hockey, H, or none of these sports. There are n students in the year group. It is known that the probability of F is equal to 3/7. The probability of H given G is 1/3. f is independent of h and g. For part A, we have to show that the probability of f and h and g is equal to 1/7 times the probability of g. For part A, we have the probability of f and g and h, and what this is the same as is the probability of f multiplied by the probability of g and h. So the probability of f will be multiplied by the probability of g and h, and the probability of g and h, that's given by the probability of g multiplied by the probability of h given g. So we have 3/7 for the probability of f multiplied by 1/3, which is the probability of h given g, and we multiply this by the probability of g. 1/3 multiplied by 3/7, that's equal to 1/7, so we have 1/7 multiplied by the probability of g, and therefore the probability of f and g and h is given by 1/7 times the probability of g. Part B. Prove that if two events x and y are independent, then x dash and y are also independent. For part B, we want to show that the probability of x dash and y is equal to the probability of x dash multiplied by the probability of y. We note that x and y and x dash and y are mutually exclusive. They cannot happen at the same time. And if x and y are independent, that means the probability of x and y is equal to the probability of x multiplied by the probability of y. Here we have our Venn diagram x and y. Here we have the probability of x and y dash. Here we have the probability of x dash and y, and the intersection is given by x and y. What doesn't go in these sets is x dash and y dash. So the probability of x dash and y, that's equal to the probability of y, so that's the entire circle of y, subtract the probability of x and y. So we have the probability of y subtract the probability of x and y, which we have said is the probability of x multiplied by the probability of y. So we subtract the probability of x multiplied by the probability of y. What we can do is factorize out a probability of y, and so what we'd have inside the bracket is 1 subtract the probability of x, and 1 subtract the probability of x, that's the probability of x dash. So we have the probability of x dash multiplied by the probability of y. So the probability of x dash and y is equal to the probability of x dash multiplied by the probability of y. So that's what we were required to show. Part C. Hence find the value of k such that the probability of f dash and h and g is equal to k multiplied by the probability of g. Well, the probability of f dash and g and h, that's equal to the probability of f dash multiplied by the probability of g and h. Now the probability of f dash, that's equal to 1 subtract the probability of f, and the probability of g and h we found earlier, that was the same as the probability of g multiplied by the probability of h given g, which is the same as 1/3 times the probability of g. So we multiply by a third times the probability of G. Now, we know what the probability of F is from the question. That was 3/7. So 1 subtract 3/7, that is 4/7, and we multiply 4/7 by a third multiplied by the probability of G. 4/7 times by a third is 4/21. We then multiply this by the probability of G. And therefore, the probability of F dash and G and H is equal to 4/21 multiplied by the probability of G. So K is equal to 4/21. Part D, show that C is equal to 4/3 A. First of all, we know for part D that the probability of F dash and G and H, that's equal to C over N. If we go back to our Venn diagram, we have N in total, and what we are after is the probability of not being in F, so that's outside of this circle, and then G and H, which is this intersection of C, which is why the probability of F dash and G and H is equal to C over N. What we can now do is find out the probability of G. For the probability of G, we've got this B, this 5, and the A and the C being added together, and then we divide by the total N. So the probability of G is equal to 5 plus A plus B plus C over N. And what we can now do is use the result we found in part C, leaving us with C over N equals 4/21 multiplied by 5 plus A plus B plus C over N. And what we can also find out is the probability of H given G. So given G, how many is H? Well, that will be the A and the C added together. So the probability of H given G is equal to A plus C over 5 plus A plus B plus C. So now we know what that is. We also know from the question the probability of H given G is a third. So we can set this result equal to 1/3. And if I cross multiply, you will find 5 plus A plus B plus C equals 3 multiplied by A plus C. So what we can now do is, from this equation, we know what 5 plus A plus B plus C is. That's 3 multiplied by A plus C. So we replace as necessary, and that leaves us with C over N equals 4/21 multiplied by 3 multiplied by A plus C over N. And if I multiply through by 21, the ends cancel on both sides, and then if I do the 4 times by the 3 times by the A plus C, what we will be left with is 21 multiplied by C equals 12 multiplied by A plus C. So we have 7C equals 4A plus 4C, leaving us with C equals 4/3 A. Given further that the probability of F given H is a fifth, for part A we have to find an expression for D in terms of A, and hence deduce the maximum possible value of A. So what we are told is the probability of F given H. So given H, how many of those are F? Well, we have the A and the D out of all the H's. So the probability of F given H, that's equal to A plus D over A plus C plus D plus 16. And therefore this result is equal to 1/5. But we know that C is equal to 4/3 A. So we have A plus D over A plus 4/3 A plus D plus 16 equals 1/5. And if we cross multiply, we have 5 lots of A plus D equals A plus 4/3 A plus D plus 16. So if we simplify all this, we have 5A plus 5D equals 7/3 A plus D plus 16. Rearranging, we have 4D equals 16 subtract 8/3A, from which we can conclude D is equal to 4 subtract 2/3 A. But we also know from the question that A, B, C, D and E are non-negative integers. So because D is greater than or equal to 0, 4 subtract 2/3 A is less than or equal to 0, which means 6 is less than or equal to A, which means the maximum value of A is 6. Part F, determine the possible values of n. What we know for part F is that C is equal to 4/3 A. And as A, B, C, D and E are positive integers, A must be either 0, 3 or 6. Let's think about why. If A was say 2, then we have 4/3 times by 2, which is not an integer. At least with A equaling 0, 3 or 6, that will force C to be an integer. And we know that the maximum value of A is 6. Now, what we know is that the probability of H given G is A plus C over A plus B plus C plus 5. And we can set this equal to 1/3. So, setting it equal to 1/3 and then cross multiplying, you'll find 3 multiplied by A plus C is equal to A plus B plus C plus 5. So let's simplify this. Well, we would have B plus 5 equals 2A plus 2C. But we know what C is. That's equal to 4/3 A. So we have B plus 5 equals 2A plus 2 multiplied by 4/3 A. And if we simplify, B is equal to 14/3A subtract 5. Now let's think about the case when A is equal to 0. When A is equal to 0, B is negative 5. We want positive integers, so this is impossible. Now, when A equals 3, B, that will equal 9. And when A is equal to 6, B is equal to 23, which are integers. But what we need to do is find the value of n. Now, the probability of f, that's equal to A plus B plus D plus 22 over n. So, we have 1 over n multiplied by, now let's leave all this in terms of A. We have A plus B, and B we know to equal 14/3A subtract 5, plus D, and D we found earlier to be 4 subtract 2/3 A, and then we add on the 22. And if I simplify this, I get 21 plus 5A over n. So, I've got the 21 plus 5A over n. That's the probability of f, and I set this equal to 3/7. And therefore n is equal to 7/3 multiplied by 21 plus 5A. So, I know that A can either be 3 or 6. It can't equal 0 because that will give B equals negative 5. So when A equals 3, n is equal to 84, and when A is 6, n is equal to 119. These are the values of n we require. Question number 6. In this question you may assume the following formulae for the volume and curved surface area of a cone of base radius r and height h of a sphere of radius r. For a cone, the volume is given by 1/3 pi r squared h, and the curved surface area is given by pi r multiplied by h squared plus r squared square rooted. For a sphere, the volume is given by 4/3 pi r cubed and the curved surface area is given by 4 pi r squared. Figure 3 shows the design for a garden ornament. The ornament is made of a hemisphere on top of a truncated cone. The truncated cone has a base radius 2r centimeters, top radius r centimeters, and height 4r centimeters. The hemisphere has radius r centimeters. Given that the volume of the ornament is 2100 pi centimeters cubed, for part A we have to show that r cubed is equal to 3150, subtract 14 r cubed. Now before we do anything else, if we take a look at this diagram, we can see this top circle has a radius half of this bottom circle, which means that if this height is 4r, the total height of the cone will be 8r centimeters, meaning the smaller cone has height 4r centimeters, and that's through the scale factor of 2. Therefore, for part A, we can begin by working out the volume of the hemisphere. That's a half times by 4/3 pi r cubed, which is 2/3 pi r cubed. The volume of the truncated cone, that's equal to pi over 3 multiplied by 2r cubed multiplied by 8r. So this is the larger cone, and then we subtract the smaller cone. So we would subtract from this pi over 3 r cubed multiplied by 4r, and that gets us 28 over 3 pi r cubed. So now what we need to do is add those volumes together and set it equal to 2100 pi. So we have 28 pi r cubed over 3, which is the truncated cone, plus the hemisphere 2 pi r cubed over 3, and this is equal to 2100 pi. If I multiply through by 3, I have 28 r cubed plus 2 capital R cubed equals 6300, and if I rearrange for capital R cubed is equal to 3150, subtract 14 r cubed. Part B, find an expression involving d capital R over dr in terms of r and or capital R. What we can do is differentiate implicitly. If I differentiate big R cubed with respect to little r, that's 3 big R squared multiplied by d big R over d little r. And if I differentiate the right hand side, end up with negative 42 r squared. So therefore, d big R over d little r is equal to minus 14 r squared over big R squared. The base of the truncated cone of the ornament is fixed to the ground. We have to show that the visible surface area of the ornament, 8 centimeters squared, is given by A equals 3 root 17 subtract 1, all multiplied by pi r squared plus 3 pi big R squared. And the visible areas are shown here. We've got the top bit of the hemisphere. We've got the red bit, which is the bit that sticks out, and then the bit underneath the hemisphere is shown in blue. So the coloured region is the region that is visible. So therefore, for part C, the area A is equal to, well, if I begin by thinking about the top bit of the hemisphere, that has area half of 4 pi r squared, so that's equal to 2 pi r squared. And then we've got the bit in blue, that's equal to pi multiplied by big R squared subtract little r squared. And then we add on to this the bit in red. And for the bit in red, we have to consider this curved surface area being pi r multiplied by h squared plus r squared square rooted. So the way we can think about this is big cone subtract little cone. And therefore, we would add on pi multiplied by 2r multiplied by the square root of 8r squared plus 2r squared subtract pi times r times by the square root of 4r squared plus r squared. So let's try to simplify all of this. So we end up with 3 pi r squared subtract pi r squared plus 2 pi r multiplied by 2r times the square root of 17, which is from here, and then we subtract pi r multiplied by r times by root 17. So simplifying even further, we have 3 pi r squared subtract pi r squared plus 4 pi r squared root 17 subtract pi r squared root 17, which simplifies to 3 root 17 subtract 1 times pi r squared plus 3 pi r squared. Part D, hence show that dA over dr is equal to gamma pi r subtract delta pi r squared over r, where gamma and delta are real numbers to be determined. Well, what we have to do is differentiate implicitly this function of a. So dA over dr, that's equal to 2 multiplied by 3 times root 17 subtract 1 times pi r plus 6 pi r multiplied by dr over dr. So we have the 2 times by 3 root 17 subtract 1 pi r, and then we add on to this 6 pi r multiplied by dr over dr, which we have found here. So we multiply by negative 14r squared over r squared, which will simplify to 2 multiplied by 3 root 17 subtract 1 pi r subtract 84 pi r squared over r. And therefore we can conclude gamma is equal to 2 times by 3 root 17 subtract 1 and delta is equal to negative 84. Figure 4 shows a sketch of A against R for R being greater than or equal to 0. There is a local minimum at R equals 0 and a local maximum at the point M. The overall minimum point is at the point N, where the gradient of the curve is undefined. For the first part of part A, we have to determine the R coordinate of the point N. Well, for the first part, at N, R is equal to 0. And if I set r equal to 0, I have 3150 subtract 14 r cubed equals 0. And if I solve for r is equal to the cube root of 3150 over 14. We now have to explain why for the ornament r must be less than this value. Well, for values of r greater than this, r will be negative, which is not possible for the ornament. Part F, show that the r coordinate of the point M is the cube root of p multiplied by 3 root 17 subtract 1 cubed over 3q squared plus 3 root 17 subtract 1 cubed, where p and q are integers to be determined. For part F, M is a local maximum. In other words, we need to set dA over dr equal to 0. So we have 2 multiplied by 3 root 17 subtract 1 pi r subtract 84 pi r squared over r equals 0. So now let's try to simplify this. Well, if we attempt to simplify, let's divide through by 2, so we end up with 3 root 17 subtract 1 r equals 42r equals 0. Next, let's take the negative 42r to the right hand side, leaving us with 3 root 17 subtract 1r equals 42r. Let's now cube, so we end up with r cubed multiplied by 3 root 17 subtract 1 cubed equals 42r cubed. And we know what r is, so r that was found to equal 3150 subtract 14r cubed. So we have 3150 subtract 14r cubed multiplied by 3 root 17 subtract 1 cubed, and that's equal to 42r all cubed, which is 74,088 r cubed. So if I multiply the 3150 by this bracket, we end up with 3150 multiplied by 3 root 17 subtract 1 cubed, and if I multiply negative 14r cubed by this bracket, we end up with negative 14r cubed multiplied by 3 root 17 subtract 1 cubed, and this is equal to 74,088 r cubed. So if we rearrange, you will find 3150 multiplied by 3 root 17 subtract 1 cubed equals r cubed multiplied by 74,088 plus 14 multiplied by 3 root 17 subtract 1 cubed. And if we simplify even further, we end up with 225 multiplied by 3 root 17 subtract 1 cubed equals r cubed multiplied by 5,292 plus 3 root 17 subtract 1 cubed. So r cubed is equal to 225 3 root 17 subtract 1 cubed over 5,292 plus 3 root 17 subtract 1 cubed. And we can rewrite this term here as 3 times 42 squared. And if we now cube root, we end up with the cube root of 225 plus 3 root 17 subtract 1 cubed over 3 times 42 squared plus 3 root 17 subtract 1 cubed. So we see that P is 225 and Q is 42. Question 7. A sequence of non-zero real numbers a1, a2, a3, etc. is defined by an plus 1 equals p plus q over an, where n belongs to a set of natural numbers. P and q are real numbers with q not equaling 0. It is known that one of the terms of this sequence is a. The sequence is periodic. Part A. Determine an equation for q in terms of p and a such that the sequence is constant of period/order 1. So for part A, we have our sequence as shown here, and what we require is for an plus 1 to equal an, and because we know one of the terms in the sequence is a, these need to equal a. So we've got p plus q over a equaling a. And if I rearrange for q, you will find q to equal a squared subtract ap. Part B. Determine the value of p that is necessary for the sequence to be of period/order 2. So for part B, we've got a1, the first term. For the second term, a2, that's equal to, using our sequence, p plus q over a1. The next term, a3, that's equal to p plus q over a2, and I know what a2 is, so I have a3 equaling p plus q over p plus q over a1. Now, for a period of 2, a1 must equal a3. So I need to set this result equal to this result, meaning we have p plus q over p plus q over a1 equaling a1. And if I multiply through by p plus q over a1, we end up with p lots of p plus q over a1 plus q equaling A lots of P plus Q over A1. And if I multiply through by A1, I have A1 P squared plus PQ plus A1Q equaling A1 squared P plus A1Q. If I rearrange, you will find A1 P squared plus PQ subtract A1 squared P equals 0, which then means that P lots of A1P plus Q subtract A1 squared is equal to 0. And if P equals A1 squared subtract Q over A1, then the sequence is constant, so the value of P we require is 0. Part C, give an example of a sequence that satisfies the condition in Part B but is not of period/order 2. Well, for Part C, we require the sequence of order 1. So if I think about something like an plus 1 equals q over an, with a1 equaling a, then q will equal a squared, which means the sequence is constant, so we've got a, etc. for our terms in the sequence. Part D, determine an equation for q in terms of p only such that the sequence has period/order 4. What we need to do is follow similar steps to what we did in Part B. So we need to find A5. So for Part D, we've got A1. A2, we know that's given by P plus Q over A1. For A3, that's equal to P plus Q over A2, which is given by P plus Q over P plus Q over A1. And A4, that's equal to P plus Q over A3, so we have P plus Q over P plus Q over P plus Q over A1. And A5 then, that's equal to P plus Q over A4, so we have P plus Q over A4, which is P plus Q over P plus Q over P plus Q over A1. So for a period of 4, A1 is equal to A5. So we have A5, which is equal to A1. And if I multiply through by this P plus Q over P plus Q over P plus Q over A1 on both sides, we end up with P lots of P plus Q over P plus Q over P plus Q over A1 plus Q equals A1 lots of P plus Q over P plus Q over P plus Q over A1. And what we will do at this point is multiply through by P plus Q over P plus Q over A1. And if I do that, on the left hand side I've got P lots of P plus Q over P plus Q over A1 plus Q multiplied by P plus Q over P plus Q over A1. And on the right hand side we have A1 lots of P plus Q over P plus Q over A1 plus Q. If I now multiply through by P plus Q over A1, we end up with, on the left hand side, P lots of P plus Q over A1 plus Q lots of P plus Q over A1 plus Q lots of P plus Q over A1 plus Q. And if I multiply through by A1, well, on the right hand side we have A1 lots of P plus Q over A1 plus Q lots of P plus Q over A1, and multiplying through by A1. On the left hand side we have P lots of A1P plus Q times by A1P plus Q lots of P lots of A1P plus Q plus A1Q. And if I do the same thing on the right hand side, I have A1 lots of A1P plus Q plus A1Q plus Q lots of A1P plus Q. So if I expand, I end up with A1P to the 4 plus P cubed Q plus 3A1P squared Q plus 2Q squared P plus A1Q squared on the left hand side, and on the right hand side I have a1 squared p cubed plus 2a1 p squared q plus a1 squared qp plus a1 squared. And if I simplify, I end up with a1p to the 4 plus p cubed q plus 2a1p squared q plus 2q squared p, subtract a1 squared p cubed, subtract 2a1q squared qp equals 0. So I've got p lots of a1 times p cubed plus p squared q, subtract p squared a1 plus 2a1pq plus 2q squared, subtract 2a1 squared, that's equal to 0. So if I factorise, I have p lots of a1p plus q subtract a1 squared, lots of p squared plus 2q, and this is equal to 0. So if I have p equals 0, that gives me order 2. I have a1p plus q subtract a1 squared equals 0, that gives order 1. And if I have q equals negative p squared over 2, that gives me order 4.